Okay, so in the last few videos we have learned about cosets of a subgroup in a group. We have learned about how cosets partition a group, and using that idea we have proved the first important theorem of the course, which was Lagrange's theorem. And remember that Lagrange's theorem says that if G is a finite group and H is a subgroup of G, then the order of H divides the order of the group. So recall, I am going to start with this. Lagrange's theorem says the following. So if G is a finite group, and H is a subgroup of G, then we have the order of H divides the order of G. And we, in fact, we proved this by using counting formula, which is a more precise statement about the orders of G and H. So not only does order of H divide A, order of G, we have this counting formula. Remember, the symbol G colon H stands for index of H in G, which is the number of left cosets of H in G. So the ratio of the order of the group divided by order of H is precisely the number of left cosets. So this is a very important formula, and Lagrange's theorem is a very important theorem. And in order to explain how we use this, let me do two problems in this video. So I want to illustrate the use of these results. Problem 1 is, let P be a prime number and let G be a group of order P. So G is a prime number and P is a prime number, G is a group of order P. Show that G is cyclic. Show that G is cyclic. So recall that a cyclic group is a group which is generated by, cyclic means generated by a single element. Okay, and I will recall this definition again in the solution. So if a group has order a prime number, then it is a cyclic group. So let's see how to solve this. So because G has order a prime number and 1 is not a prime number, since 1 is not a prime number, G contains an element A which is different from E. This is because if G does not contain any element different from E, then order of G is 1, because G is just the set consisting of E. But then order of G is 1. At the same time, we know order of G is a prime number, so it can't happen. So now consider the subgroup. Consider the subgroup H generated by A. So remember, H is all elements of this form, E, A squared, and so on. And because it's a finite group, it will stop somewhere, and inverses of A will also be included in this. So I'm not going to write A power minus 1 and so on, because some A power positive integer will be equal to A power minus 1. Now Lagrange's theorem says what? Gives order of H divides order of G, and order of G is a prime number. Order of G is a prime number, and order of H divides it. But because P is a prime number, only numbers that divide a prime number are 1 and that prime number. So order of H is either 1 or order of H is P. Clearly order of H cannot be 1. Right? Why can't this happen? Because H contains A and E which are distinct. So H cannot be order 1 group. So this must be the case. But if H has order P and G has also order P, this means H equals. But note that H is cyclic by definition. It is a group generated by, it is the subgroup generated by a single element. So it is a cyclic group by construction, and H is equal to G, so G is cyclic. That's all. So we have solved the problem. If you have a group of order, prime order, it is cyclic automatically. You might wonder, what about groups that are not of prime order? So does there exist a group of order 4 that is not cyclic? See, 4 is not a prime number, so the problem here has nothing to say about a group of order 4. It however says that a group of order 2 must be cyclic, a group of order 3 must be cyclic, a group of order 5 must be cyclic, 7, 11 and so on. But 4 we don't know. Does there a group of order 6 which is not cyclic? We know a group of order 6 that is not cyclic. Right? We know that, right? Because we can take S3, which remember in our new notation has this form. This has order 6, but elements have all order 1, 2 or 3. Okay, so this is I will leave this as an exercise for you. It's a very easy exercise. It's something you should do, and we have done enough to conclude that it is not cyclic. But I haven't explicitly talked about a group of order 4 that's not cyclic. That I will come back to later in the course. Okay, so this is anyway, this is a digression. The problem was to show that any group of order equal to a prime number is cyclic, and we have used it. It becomes an immediate, the solution is immediate if once you use the Lagrange's theorem. So Lagrange's theorem is very powerful. The point of the problem is to illustrate that. One more problem I want to do just to illustrate more about cosets. So let's take a group homomorphism. Phi is a group homomorphism. Show that order of G, okay, so again assume G is finite. So whenever we talk about order, we have to assume it's finite. Show that order of G is equal to product of the order of kernel phi and image phi. Remember, kernel phi is the set of elements of G which map to the identity element of G prime. Image phi is simply the image of the function. All elements of G prime that have pre-images in G. So show this. Okay. So this is also a problem which illustrates important features of group homomorphisms as well as application of the notion of cosets. So I'm going to give a name for this. So let n equal kernel phi. So recall that when we defined group homomorphisms, we showed that kernel of a group homomorphism and image of a group homomorphism or subgroups. Not only that, after I defined normal subgroups, I showed that kernel is a normal subgroup. So we know that N is a normal subgroup of G, and we also know that image, let H prime be image of phi. Instead of writing kernel phi, image phi all the time, I am giving them names. Image phi is a subgroup of, so H prime is a subgroup of G prime, and in general it's not a normal subgroup, okay, as you should think of an example. So we want to show that, we have to show what? Order of G is equal to product of order of N and order of H prime. So let's show this. So what I will do is, we will show the following. Before that, before I write that, I am going to recall for you. If A and B are in the group G, phi of A equals phi of B if and only if B is A n for some in n, some n in small n in n. Why is this? This was done by us, but let's quickly recall this. So I will write it separately. Phi of A is equal to phi of B. That means phi of A B inverse, let me write this as A inverse B is E G prime. Okay, this is because phi of A inverse times B is phi of A inverse times phi of B. Phi of A inverse is phi of A whole inverse. So these are inverses of each other, and multiplying them you get identity element of G prime. Okay, I have done many examples of this, so I am not going to write down the details. But this, if A inverse B goes to E G prime, by definition A inverse B belongs to N. That means B belongs to A n. Right? This is exactly the statement. And note that if this happens, B plus B, if B is in A inverse B is in N. If A inverse B is in N, by definition phi of A inverse B is E G prime. And if phi of A inverse B is E G prime, then phi of A must be equal to phi of B. So these are implications, go backward also. So this is the if and only if statement. This is the statement that An equals Bn. So if B is equal to An must be equal to the left coset. Recall that An is the left coset A times small n for all small n. Bn is B times small n for all n. Remember that if B is equal to An is an element of A capital N, B is an element of B capital N, because you can take small n to be the identity element. So B is certainly in Bn. So An and Bn have a common element, namely B. Hence they must be equal cosets. Remember, two left cosets are either identical or they have nothing in common. So we will use this to solve the problem. Now let's recall the problem. We are trying to show that cardinality of G, or namely the order of G, is equal to order of N times order of H prime. So this is the product, okay, product of two numbers. So why is this true? I am going to say that, so I will take the set of, consider, so I will write it here, consider the set of left cosets of N in G. Okay, so this set is this is denoted by I am introducing new notation for you, and this is this anticipates our definition of quotient groups later. G mod n, it is read as G mod n. Okay, that's how you read this. G mod capital N is the set of left cosets. For now it is simply a set. So consider a map consider the function from the left cosets to H prime. Okay, H prime, remember, is the image of phi. What is the left coset? So what is the function I want to consider? I'll take an element an. Left cosets are of the form an, and I will map it to phi of a. Okay, so this is the function. I'm defining the function an going to this. So this is the function f. So f of an is just phi a. I claim that we will show that f is a bijection. So f is a bijection. What does this mean? So first we want to show f is onto. F is onto. Why? So you give me any element of H prime. In order to be onto, a function has to have a pre-image for every element in H prime. So you give me an element of H prime. What is an element of H prime? Remember, H prime is the image of phi. So let phi of a be in H prime. H prime is the image, so it only contains elements of the form phi a where a is in G. Then what is f of an? F of an is precisely phi a. Right? By definition, f of an is the function which f of an is phi a. F sends an to phi a. So if phi a is in H prime, f of an is phi a. So every element of H prime is in the image. So f is onto. Now we will show that f is 1 1. What is the meaning of 1 1? If two elements under f map to the same element, those two elements are equal. So suppose that f of an equals f of bn. So take two cosets which have the same image under f. This means phi a is equal to phi b, because fan is by definition phi a and fbn is by definition phi b. And then I have checked earlier that if phi a equals phi b, an equals bn. By the above argument, we conclude, because phi a equals phi b implies an equal to bn. So we have concluded that f is 1 1 also. F is onto, we checked. F is 1 1 also, we checked. So f is a bijection. So f is a bijection between two sets. What does this mean? So f is a bijection between G mod n and H prime. If you have a bijection between two sets, the two sets must have the same number of elements. The number of elements in Gn, in G mod n, is equal to the number of elements of H prime, which is what we denote by order H. But what is the number of elements in Gn? Number of elements in Gn, Gn being the set of left cosets, number of elements in Gn, G mod n, is precisely the number of left cosets of n in G, which we denote by this symbol G colon n in brackets. So G colon n is equal to the cardinality of H prime. But what is G colon n? By counting formula, which I recorded at the beginning of this video, counting formula says G mod n is equal to cardinal order of G mod order of n, which is equal to order of H prime, which implies order of G is equal to order of n times order of H prime as desired. right? This is exactly what we wanted. The problem asked to prove that order of G is equal to order of kernel phi times order of image phi. Kernel phi was denoted by n, image phi was denoted by h prime. So order of G is equal to order of kernel phi times order of h prime. So that completes the solution. So in this two problems, I hope you understood how to use the counting formula and Lagrange's theorem, and using these we are able to conclude very strong statements about groups. So I'll stop the video here, and in the next video I'm going to start with my definition of quotient groups. Thank you.